There are many different kinds of means. Usually, when we say mean, we refer to the arithmetic mean. It is the sum of a few real numbers divided by the number of numbers. However, there is another type of mean that most of us don't really learn at school, the geometric mean. Instead of adding up all the numbers, we multiply them and root the product according to the number of numbers. Interestingly, there is a relationship between these two means, an inequality that is true no matter what the values of x, y, and z are. This inequality serves as a useful tool for many problems down the line. Let's start small. Can we show that the arithmetic mean of two non-negative numbers, a and b, is always greater than or equal to the geometric mean? Let's try to work backwards from the result. We can multiply both sides by 2, removing the fraction. If we bring 2 square root ab to the other side, we will get a minus 2 square root ab plus b, which can be factorized to give square root a minus square root b squared. This term is always more than or equal to 0 since it is a square. Notice that it is 0 only if a is equal to b. Also, it only holds if a and b are non-negative, since they are inside square roots. Thus, the AM-GM inequality is true for two variables. Let's apply this knowledge to a problem. For positive real numbers a and b, find the minimum value of a over b plus b over a. From the AM-GM inequality, we know that a over b plus b over a over 2 is greater than or equal to the square root of a over b times b over a, which is equal to 1. Thus, a over b plus b over a is greater than or equal to 2, 2 being the minimum value. We can see that the AM-GM inequality has kind of an effect of changing a sum into a product through an inequality. The AM-GM inequality is also true for more variables, as long as each variable is more than or equal to 0. We'll try to prove this later in the video. For now, let's take a look at another example. Before we start, it's important to note that it is completely normal to feel stumped by these questions. They are meant to be played around with, and most people won't solve it on their first try. With that being said, here's our problem. A plus b plus c is equal to 1. Prove that 1 plus a times 1 plus b times 1 plus c is greater than or equal to a times 1 minus a times 1 minus b times 1 minus c. Let's try to analyze the question. In the right side, there is a product of 1 minus a, 1 minus b, and 1 minus c, which indicates that we could use the AM-GM inequality with this being similar to the GM. Using the same idea of interchanging sums and products, we can consider 1 minus a plus 1 minus b, which is equal to 1 plus 1 minus a minus b, which is equal to 1 plus c according to our condition. Sometimes we may not know how we're going to use the condition, and so we need to do something with the actual equation first before using it. Now this resembles the left side of the equation in the question. Applying the AM-GM inequality, 1 plus c is greater than or equal to 2 times square root of 1 minus a times 1 minus b. Similarly, 1 plus a is greater than or equal to 2 times square root of 1 minus b times 1 minus c, and 1 plus b is greater than or equal to 2 times square root of 1 minus a times 1 minus c. Multiplying everything together, we get 1 plus a times 1 plus b times 1 plus c is greater than or equal to 8 times square root of 1 minus a squared, 1 minus b squared times 1 minus c squared. Thus, 1 plus a times 1 plus b times 1 plus c is greater than or equal to 8 times of 1 minus a times 1 minus b times 1 minus c, which is our desired result. Sometimes we need to play around with the inequality to see which terms are suitable to be used in the AM-GM inequality. Now, how do we know that the AM-GM inequality works for more than two variables? Let's first prove that it works for four variables. According to the AM-GM inequality for two variables, replacing a with p plus q over 2 and b with r plus s over 2, we get p plus q plus r plus s over 4 to be greater than or equal to the square root of p plus q over 2 times r plus s over 2. Notice the arithmetic means on the right side. We can apply the AM-GM inequality one more time and get the square root of pq times the square root of rs, which is equal to the fourth root of pqrs. Thus, the AM-GM inequality is valid for four variables. Using the AM-GM inequality for four variables, can you prove that it is true for 8 variables? In fact, repeating this process infinitely, we can see that the inequality is true for numbers of variables which are powers of 2. Now, how do we prove that it's true for the others? Let's assume that it is true for n variables. Thus, the arithmetic mean of n variables, a1 to an, is greater than or equal to their geometric mean. Since the variables can be any non-negative number, let's replace an with the geometric mean of a1 to an minus 1. On the right side, we can see that this is equal to the n minus 1th root of a1 to an minus 1. You can try to prove this using rules of indices. Now we can bring the n over to the right side by multiplying both sides by n, and bring over the geometric mean to the right side as well. This gives us the sum of a1 to an minus 1 to be greater than or equal to n minus 1 times the geometric mean. Bringing n minus 1 to the left side, we have proven that the AM-GM inequality is valid for n minus 1 variables. If the inequality is true for any number of variables, it will be true for the number before it. Thus, since the AM-GM inequality is valid for 4 variables, it is also valid for 3 variables. Since it is valid for 8 variables, it is also valid for 7, which implies that it is valid for 6, and so on. Thus, eventually all the natural numbers of variables have been covered, and the AM-GM inequality is true for any number of variables. With the AM-GM inequality, you now have a powerful tool to solve many Math Olympiad problems.